When we first introduced multi-step synthesis for this alpha carbon chemistry chapter, I mentioned that there are two patterns that are special to this chapter and that make the multi-step syntheses in this chapter a little bit more manageable. The first pattern that we saw were creating di-functionalized compounds. And we saw the three patterns for that involving the aldol addition, Claisen condensation, and the storic-enamine synthesis. And in the last three videos, we have explored exercises, multi-step syntheses that involve di-functionalized compounds. The second pattern, that was just the first pattern, those di-functionalized compounds. The second pattern is putting an alkyl group, putting carbon chains on both the alpha and the beta carbons of alpha-beta unsaturated systems. So, for example, if you had this cyclohexanone, but it was alpha-beta unsaturated, so you have a pi bond between the alpha carbon and the beta carbon, you can put two different R groups on this. One, so we have the alpha carbon and the beta carbon. You could put an alpha carbon on the beta carbon, an alpha group on the beta carbon, and here maybe I'll just put an R, because it could be any alkyl group. And you could put an alkyl group on the alpha carbon. So that could be the same thing, it could be a different thing. You can alkylate, put a hydrocarbon chain on both the alpha and the beta carbons. So how would you do that? Well, we know that this beta carbon is an electrophile that can be attacked by weak nucleophiles. That's the Michael reaction. And we saw if we're trying to add a carbon, we can use a weak carbon nucleophile. We saw when we first talked about the Michael reaction that we can use a Gilman reagent. So you'd sort of have this R group, you'd have two of them attached to copper lithium as your first step, and then your second step is usually water. Now let's wait a second before we apply the water here. Let's see what sort of happens. Now, with these Gilman reagents, the carbon, represented by the R, is bonded to the copper. And so because the copper is a metal, now it is kind of in the middle of the periodic table, so it has decent electronegativity, but because it's a metal, its electronegativity is very low relative to nonmetals. And so it gives its electron density away to these carbon chains, which then become nucleophiles. But because the copper is in the middle, it's a transition metal, so it's not all the way to the left in the periodic table, it has a relatively high electronegativity for a metal. And so this bond is not as polar as, for example, in a Grignard reagent. And that makes these R groups nucleophiles, but weak nucleophiles. And weak nucleophiles prefer the electrophilic beta carbon to the carbonyl carbon, as we've seen before. So this R group would attack here, push these electrons up toward the positive charge of the carbonyl, and that kicks the electrons onto the oxygen. So that after that first attack by the Gilman reagent, you would end up with this intermediate. Now notice we've added our carbon onto our alkyl group onto the beta carbon. Now we just have to add a different carbon chain onto the alpha carbon. Well, notice what we have. We have a nucleophile. This alpha carbon has a pi bond on it, which can function as a nucleophile. So if we can take whatever carbon we want and do an SN2 reaction. So for example, well, let's just have this R group here. It will have a halogen on it as a leaving group. These electrons can snap back down. They're attracted to the slightly positive carbon there. That pushes these electrons to become a nucleophile that attack the carbon of an alkyl halide and kick the halogen leaving group off. Remember that X is chlorine, bromine, or iodine. And you could see that you would end up with this product, this alpha-beta alkylated product. So in general, you can turn an alpha-beta unsaturated compound into an alpha-beta dialkylated compound. So you can put an alkyl group on the alpha and the beta carbons, in general, in a two-step procedure. The first step is using a Gilman reagent. Whatever carbon you want on the beta position, you put in the Gilman reagent, so that dialkyl lithium cuprate. And then whatever you want on the alpha carbon, you just make an alkyl halide out of it. And the alpha carbon nucleophile will attack that in an SN2 reaction. And so we can put alkyl groups on the alpha and beta carbons of any alpha-beta unsaturated aldehyde or ketone by using a Gilman reagent followed by an alkyl halide. Okay, so let's apply that idea to the molecules in exercise 2254. We see that we have an alpha-beta unsaturated ketone. So let's think about what we want on the alpha position and the beta position. We have a methyl group on the beta position. We have a benzyl group. Remember, when benzene is a branch, it's called phenyl, when it's just the ring. But if it's the benzene and the benzylic carbon, so benzene and one other carbon, that's called a benzyl branch. So we have a methyl group on the beta carbon, a benzyl group on the alpha carbon. So we can do this in two steps. First, we can treat this with a Gilman reagent. Because the group that we want to add on the beta carbon is a methyl group, we'll have the methyl, two of those, copper lithium. That will give us this product. And then we can react that, use this nucleophile to do an SN2 reaction. Right? Remember, this weak nucleophile will be attracted to that beta electrophile. Then we can do an SN2, use this nucleophile here to do an SN2 reaction. We want a benzylic group on here, so we can have that blue group, but on it, just put a leaving group to allow the SN2 reaction to happen. So here, we'll put that the carbon in the Gilman reagent on the beta position, and then when this snaps back down, this can attack that carbon there, and that will put the benzylic group on the alpha position. And that gives you your product. So overall, first, dimethyl lithium cuprate, Gilman reagent, followed by this alkyl halide. And that would be called benzyl bromide. And those two simple steps can accomplish what would at first look like a really daunting transformation. Okay, let's apply that same thinking to this next exercise. So here we have an alpha-beta unsaturated aldehyde, right? You have the carbonyl carbon, next to that is your alpha carbon, and next to that is your beta carbon, so alpha-beta unsaturated. And what you notice is that we add two groups onto that. Onto the beta carbon, let me translate that over. Onto the beta carbon, we have a methyl group. And onto the alpha carbon, we also have a methyl group. So we can do that in two steps. And now that we've seen the mechanism a couple times, I'm just going to write it out from the perspective of synthesis. First, you do the Gilman reagent. You use whatever group is on the beta carbon. That's a methyl group, so dimethyl lithium cuprate. And second, you do an SN2 reaction. You take whatever carbon chain is on the alpha carbon, so that's just a methyl group, and you put a leaving group on it. I'll put chlorine, but it could be bromine or iodine, any leaving group. What that will do is alkylate the alpha and beta positions. the beta position will have whatever is in the Gilman reagent. So that methyl group there. And the alpha position will have whatever is in the alkyl halide. So another alkyl group here. Okay, well, we're almost at our product. The only difference is in the molecule we have right now, we have a double bond to an oxygen. In the final product, we have a single bond. We want to reduce the number of bonds to oxygen. That's a reduction. So we could use lithium aluminum hydride, and then followed by a water wash to help stabilize the negative charges on the oxygens that you make by doing a proton transfer. So overall, there'd be 4 steps in this reaction, in that synthesis. To create that transformation, you'd alkylate the beta position using a Gilman reagent. That's a Michael reaction. Then you would use the nucleophile you create in that enolate to alkylate the alpha position using an alkyl halide, SN2 reaction. Then we just want to reduce our aldehyde, the aldehyde that we had there. And that can be done by using a strong reducing agent like lithium aluminum hydride. And then we just follow that up with a water wash to stabilize the negative oxygens that we create. And so that recipe creates this transformation. And the key to it, the thing that simplifies it a little bit, is just noticing that you're adding alkyl groups onto the alpha and the beta carbons. Okay, let's try C. So in C, you'll notice we have an alpha-beta unsaturated aldehyde. So we have an alpha carbon and a beta carbon. And let's draw that in, the analogous carbons on the product. We have the alpha carbon and the beta carbon. What you'll notice is that the pi bond goes away. And instead, you have a carbon attached to the beta position and a carbon added onto the alpha position. So we have alkylated the alpha and the beta positions. Now you can do that in 2 steps. First, you use a Gilman reagent. Whatever is attached to the beta carbon, here it's a methyl group, you have that in your Gilman reagent, so dimethyl lithium cuprate. And then whatever is in your alpha, whatever is attached to the alpha position, here it's a methyl group, we can add that to a leaving group. So chlorine, bromine, iodine, any leaving group would be fine. You'll do an SN2 reaction to attach that. So at that point, after you do those 2 reactions, and note that whatever is in your Gilman reagent, that goes onto the beta position, whatever is in your alkyl halide goes onto the alpha position. Always do the Gilman reagent first. So what you have after that is this dialkylated compound. But here we have an aldehyde, and what we want is an acid chloride. Now we only know one way to make an acid chloride. It's from a carboxylic acid. Oops. If you had a carboxylic acid, well then you can treat this with thionyl chloride and create the acid chloride. But how do we turn the aldehyde into a carboxylic acid? Well, in the aldehyde you only have 2 bonds to oxygen. In the carboxylic acid you have 3. So you can use a strong oxidizing agent like sodium dichromate in water and sulfuric acid. And that will oxidize that aldehyde into the carboxylic acid. So that, overall, we have a 4-step procedure to make this transformation happen. First, you would use the Gilman reagent to do a Michael addition. That weak nucleophile will attack the beta carbon electrophile. That carbon is electrophilic because of resonance, slightly positive. Then you have an enolate. The double bond, the pi bond in the enolate, can act as a nucleophile in an SN2 reaction to attach a carbon chain on the alpha position. All you need is an alkyl halide. That gave us this aldehyde here, so we attached the 2 groups to the alpha and beta carbons. Now we had to worry about the functional group. We turned the aldehyde into a carboxylic acid using a strong oxidizing agent like sodium dichromate in water and sulfuric acid. And finally, once we have the carboxylic acid, we can create the acid chloride using thionyl chloride. And so that is the recipe that you would use to create this transformation. Okay, let's try D. So in D, we have an acetal, right? Carbon with an ether, with two ethers attached to it. In addition to that, we have an alpha and a beta unsaturation. So you sort of have an alpha here and a beta carbon there. Let me draw that in, the analogous carbons in the product. And what you'll notice is the unsaturation goes away, and you add two carbons there. You add a carbon to the beta position, and you add a carbon to the carbon chain to the alpha position. Okay, well, before we add those, we have to have an aldehyde or a ketone. Right? When you think back to the mechanism that we drew up here, in order to have this weak nucleophile attack the beta position, the electrons have to go to create a pi bond, and that has to push these pi bonds up onto that oxygen there. So you need a ketone to start with. So we have to hydrolyze the acetal. If you treat the acetal, remember, if you treat it with acid, and you drew the mechanism for this on a previous test, then what you'll get is the acetal will turn into a ketone. And so now we have our alpha-beta unsaturated ketone. And we can dialkylate this. We can alkylate the alpha and beta positions. First, we're going to use a weak nucleophile, a Gilman reagent, to attack the beta carbon. We have an ethyl group. So we'll have diethyl lithium cuprate. That will give us an enolate up here when that attacks the beta carbon. And that enolate can act as a nucleophile to do an SN2 reaction. So we need an alkyl halide. Here we want to attach another ethyl group, and we just use any leaving group. I'm going to use a chlorine to do an SN2 reaction on the alpha position. So that will alkylate the alpha and beta carbons of this molecule. So the ethyl group from the Gilman reagent will be added onto the beta carbon. The ethyl group from the alkyl halide will be added onto the alpha carbon. So we have this product here. Next, all we have to do is recreate the acetal. And you remember that you can make acetals out of ketones. You drew the mechanism for that on that previous test. All you need, here we have two carbons with an alcohol on each end. This is actually the antifreeze that's used in cars. It's ethylene glycol. Pets tend to find that sweet, but unfortunately it kills them, so you have to be careful that pets never drink that antifreeze. And then you just want to have an acid catalyst and remove water from the product to increase your yields using Le Chatelier's principle, and that will recreate your acetal. So you have two alcohols, and that reacts with a carbonyl to give you the acetal here. So it's a multi-step synthesis, but the meat and potatoes of it is alkylating the alpha and beta carbons. And you alkylate the beta position using a Gilman reagent first. That gives you an enolate that allows you to alkylate the alpha position by doing an SN2 reaction. So you just need an alkyl halide for the enolate nucleophile to attack. Okay, let's try E. So for E, in this one, you notice that you have an unsaturation. You don't really have an alpha-beta unsaturation because you don't have a carbonyl, but we could easily get a carbonyl out of this. Let's say we oxidize that. Now, we could oxidize it to an aldehyde or because it's a primary alcohol. This OH is bonded to a carbon that's only bonded to one other carbon. So it's a primary alcohol. If we used a strong oxidizing agent like sodium dichromate in water and sulfuric acid, we would get a carboxylic acid. But when we look at the analogous place on the final product, we see that the group added above here is a hydrogen. And so we want to keep that hydrogen there. So we want to oxidize this using a weak oxidizing agent, pyridinium chlorochromate, PCC, in dichloromethane solvent. Now if we do that, and this is just an experiment, but if we do that, then we end up having this alpha-beta unsaturated aldehyde. We have a pi bond between the alpha and beta positions. And that is exciting because we notice that the alpha and beta carbons, these alpha and beta carbons, are alkylated. We have a methyl group added to the beta carbon, and we have another methyl group added to the alpha carbon. So we can do that alpha-beta alkylation first by using a Gilman reagent. Now, on the beta position, we have, on the beta position, we have a methyl group, so that's what we put into our Gilman reagent. So a methyl group, we have dimethyl lithium cuprate. That will add, that weak carbon nucleophile will attack the electrophilic beta carbon. That'll create an enolate, which allows the alpha carbon to act as a nucleophile, and you can do an SN2 reaction with an alkyl halide. So we take whatever alkyl group we have on the alpha, we want to add to the alpha carbon, and we just turn that into an alkyl halide. We add a halogen leaving group on it so that it can participate in an SN2 reaction. That will leave us with our aldehyde and a methyl group on both the alpha and beta carbons. Now notice, the methyl group on the beta carbon came from the Gilman reagent, the methyl group on the alpha carbon came from the alkyl halide. The only thing we still have to do in order to get this final product is to replace the carbonyl, the double bond to the oxygen, with an imine. You'll remember that's an imine. And this was another reaction that you drew the mechanism for in the aldehyde and ketone chapter. To create an imine, you need to form two bonds to the nitrogen. In other words, you need a primary amine. So the nitrogen that you add has to have two hydrogens on it. Those are what get replaced in this double bond to what was the carbonyl. Well, nitrogen gets 3 bonds. This is only 2. What goes to the third one? Whatever group you want hanging off of the nitrogen in the final molecule. So here, that's a methyl group. Now you want to use an acid catalyst to that, or else the rest of your life will just be acting as a spectator of this last step. So an acid catalyst, and then remove water to increase your yields using Le Chatelier's principle. So overall, in this synthesis, there are 4 steps. The first step is using PCC in dichloromethane solvent to turn the alcohol into an aldehyde. So a weak oxidizing agent. Then we can dialkylate the alpha-beta unsaturated aldehyde, first by using a weak carbon nucleophile, in this case dimethyl lithium cuprate, and we based the carbon in this Gilman reagent on what we wanted to attach to the beta carbon in the final product. And then that creates an enolate that allows the alpha carbon to act as a nucleophile. So we just look at what we want to attach to the alpha carbon and give that carbon group a leaving group on it so that we can do an SN2 reaction. That gives us our alpha-beta dialkylated compound. And then we just would create the imine by adding this primary amine. So we'd have a methyl group, and then the nitrogen and 2 hydrogens. Notice the nitrogen is bonded to just 1 carbon, so it's a primary amine. The 2 bonds to the hydrogen get replaced by the 2 bonds to what was the carbonyl. And to make that more efficient, you use an acid catalyst, and you remove water from the products. As you remove products, Le Chatelier's principle pushes equilibrium toward the products to minimize the change. So this recipe here would create this transformation. Okay, last one. And this one has a sort of weird reaction at the very end of it that it would be excusable not quite to remember, although we have seen it before, just in a different context. So what you see here is we have an unsaturation But it isn't quite alpha beta because we don't have a carbonyl. But we can get a carbonyl. We can use PCC in dichloromethane solvent to turn that primary alcohol into an aldehyde. Now once we have that, those two carbons become an alpha and a beta carbon to that carbonyl. And so I'm going to draw those in this product. We have the alpha and the beta carbon, and what you'll notice is that we have added an alkyl group on the beta carbon and an alkyl group on the alpha carbon. In other words, we have dialkylated this. We've alkylated both the alpha and the beta carbons. And we've seen how you can do that. You can alkylate the beta carbon by using a Gilman reagent. We want to add a methyl group on the beta carbon, so we put a methyl group in our lithium cuprate, so dimethyl lithium cuprate. Whatever is in your Gilman reagent, which you use first, that's what attacks the beta carbon. That's the nucleophile that attacks the beta carbon. When it attacks the beta carbon, it creates an enolate so that the alpha carbon can become a nucleophile. And it can attach to another carbon by doing an SN2 reaction. So look at the carbon chain you want to attach to your alpha position. Take that same carbon chain and just add a leaving group. I'm going to add iodine. Any leaving group would do. And that will get attacked by the alpha carbon and form that new carbon-to-carbon bond. So you would have your same molecule, just on the beta carbon you'll have your methyl group from the Gilman reagent, and on your alpha carbon you'll have a methyl group from your alkyl halide. Okay, so we almost have the final product. The only thing that we want to get rid of is this weird carbonyl. We still want the carbon from that there. We just want to get rid of the carbonyl. And this is a sort of weird callback that it would be excusable, not quite to remember. To completely get rid of a carbonyl, you can use a zinc mercury amalgam, HCl, and heat. The place we've seen that before is when you do Friedel-Crafts acylation. So if you had, for example, an acyl chloride and you wanted to add that onto benzene, and so you use an AlCl3 catalyst, you could put that onto benzene, and then, so that's a Friedel-Crafts acylation, and then you can get rid of that carbonyl by using this reduction, this zinc mercury amalgam in HCl and heat. That's where we've seen this before, and that would give you an alkyl group on your benzene ring. And the reason why you'd go through that whole process instead of just using Friedel-Crafts alkylation is because Friedel-Crafts acylation won't undergo carbocation rearrangement. So this allows you to put an alkyl group onto a benzene ring without getting Friedel-Crafts without getting carbocation rearrangement. So if you wanted to put a primary carbon onto a benzene ring, you'd use Friedel-Crafts acylation and then reduce it using this recipe. Well, here we can use that same recipe to take this double bond to oxygen off. And so overall, you have 4 steps in this mechanism, or in this synthesis. The first step is to use PCC, pyridinium chlorochromate, and dichloromethane solvent to create an alpha-beta unsaturation, to create a carbonyl with an alpha and beta position with their unique reactivities. Then you alkylate the beta position by using the weak Gilman reagent. You alkylate the alpha position by using an alkyl halide. And finally, we get rid of the carbonyl, oxygen, by doing this reduction with the zinc mercury amalgam, so smushing those two metals together, and then using HCl and heat. And that recipe will create this transformation. So hopefully this video helps to clarify how you can use the first a Gilman reagent and then an alkyl halide to alkylate, to put a carbon chain on first the beta carbon and then the alpha carbon of an alpha-beta unsaturated system.